T2 demos. T2 demos. T2 demos. This is the first test to try to do time-lapse with the X-T4. There's the parameters. We're going 300 times. Speed up, these are JPEG frames. There's lots of problems with this, but it's fairly encouraging. I'm worried, since this is just one power zone, I'm worried about when we get to like 9 power zones, whether there's going to be enough res. But we'll see in the second demo where I do some camera projector automation, I'm calling it, that it looks pretty good. We can push from here, we can push all the way into a single tile after the fact and still like read the text, for example, which was not really true with the previous solutions. I don't know if that will still be true with 9 power zones, but we'll see. So this was a big update of almost everything, because I hadn't had this grid fired up for quite some time. I'd been working on the single ring, and then obviously just doing a Hugene run, which I wanted to run until it settled one way or the other all by itself, but I didn't really understand how the Fuji X-T4 works, and its battery died. So that's where this simulation ends. All right, so here we are pushed into a single video, also with a little bit of color grading, since the background of the CDM menus really should be brown. And the LCDs we're using are really so low quality. So I've just tried to get this to approximate, to sort of emphasize rendering what passes for true colors on the LCDs, and let the the T2 tile cases and the surrounding environment and stuff go hang. But I'm also, and this is using the Kdenlive transform effect with keyframes that are set to smooth, which is cubic splines, I think, and I'm starting to get them working. You can see that this is actually fairly smooth, and it doesn't have a lot of changing in directions that don't make a certain amount of sense given the action on the screen. So this is it. This is the first test. I've now got an order for one of these dummy battery things that connects to a charger so that it's not relying on USB power. So hopefully we'll be able to do much longer. Lots more stuff to do. Just figured I'd put the first test up. That's it. Alright, I tried to redo the ducking parameters, so there's perhaps some hope that the talking over the video sound, the audio from the video, should maybe go together a little better. We'll find out. Hey folks, welcome to the Artificial Life Advanced class. So here's the pop quiz. What's the difference between these two diamonds? And I'm focusing on the pocket chain, the squiggly loop inside of them. How are the layout of the squiggles different on the left and the right? Here's another example. Left and right. What's the difference? Can you see it? When I look at this, the ones on the right seem to have a lot more straightaways, and the one on the left is much more twisted. Here's another example. More straightaways, and in particular, right along the main axis, more sort of runways in the middle of the diamond. But the code, the pocket chain code for all 6 of these diamonds is exactly the same. So how do we get these different appearances, the more twisty and the more straight, to come out of the same piece of pocket chain code? And to understand where it's coming from, we have to look at where it came from. The one on the right is growing from a small diamond. The one on the left, the diamond immediately grows out to its final size, and then the pocket chain just fills in. And so that makes sense, right? It's got all of this space, and the pocket chain layout stuff is fundamentally random, if it can be. But with the incremental growth, the important point for me was that I didn't have to change the pocket chain expansion code at all when I developed making the diamond grow incrementally, which is one of the things that's new this time. And same code, different life history, different opportunities, different result that comes out at the end. I thought it was kind of interesting, especially because symmetries always draw our eyes, and we think, what does it mean? Does it mean something about the inherent structure? Well, it might just be the result of different opportunities. So the bigger picture for this is that if we're going to have diamonds growing, which we are, if we're going to have diamonds reproducing, which is the whole point of this artificial life creation countdown, then we're eventually going to run out of space. Artificial life demands artificial death, and we need to face that. I wanted to focus on it this time. So we're at T-7. Here's the spreadsheet. Strands and loops, that's the pocket chain. We're sort of doing, but not too terribly there. The border stuff, we've got, new versions of the border working fairly well. In fact, there's new stuff today. There's one new element, a little tip that goes just at the tips of the diamonds that helps get the contact warnings in the absolute straight directions and just generally holds things together. And the borders are looking pretty good. But the purpose of the pocket chain loops and so forth was to represent code that was going to drive the reproduction process. And none of that. HC3 sequencer, was supposed to sort of represent, the code represents the program. The HC3 sequencer represents the processor. Got none of that at all. So that is, there's some reasons for it, but it's worrisome. How long we can hold to our countdown without having to hold, we will see. On the other hand, grow to X, have a diamond that can expand on a programmatic basis, was really scheduled for T-4 or T-3, and we already have a really pretty good cut at it. So we shall see. And again, why do we need these things? Well, growing to 2 times radius, that's the very first step in the planned diamond matrix life cycle that begins with a single mother and ends with 2 daughters, then the cycle can repeat. So sequenced matrix growth is something that we didn't have before and we absolutely need. All right. Oh, and so the version of the code that we just saw here is now running on the T2 grid. There's a T2 demo out on it, about 3 minutes long, and we'll just watch a teeny little bit of it now. I do love the debeziler, I admit it. Look at that. basically I'm just stuffing more and more in until something happens. You know, sort of a stress test. So far, reasonable. So we'll see how that develops. I'm going to let it keep running for the next, I don't know, maybe a week or so. We'll see. But the second step after that, after we grow, there's this reorganization. The idea is that we're going to have to take the code, the program, and get it out of the way so that we have room within the cell to make another copy of it. And I didn't really have anything specific in mind about how that was supposed to work. There's still some questions about it, but the goal I set myself for this update, the loop operations, was supposed to be related to that. Now, I didn't really make very much progress on loop operations. Well, I didn't make any progress on loop operations, at least the way I had originally conceived it, you know, where you sort of maybe take a loop and cut it open and put some special head on it, like a locomotive on a train, and it would drag the thing elsewhere and then it would reconstitute the loop. You know, none of that. If we're still going to use that, which I'm kind of thinking we are, that is yet to come. But I had this other idea about how to navigate on the diamond, even though the HC3 grid has very limited information available about where you actually are. So let's take a look at this. All right. So this is 6 little diamonds, growing diamonds that are seeded, and they're all just bouncing around. But look how the pocket chain is growing. Oh, and see, now we got 4 of them that actually are locked up, and one of them died to make room for the other ones, which are now just sort of bouncing around and bouncing around. But look at that. The northwest quadrant, the southwest quadrant, northeast, got a southeast one over here, and so forth. So that is new. And it went in fairly well. It went in fairly easily. Okay, there we are. Yes. These are some of the screen grabs from that we just saw. So here's the 4. I can't get the screen direction right. So the 4 of those are locked against each other and the edge of the universe until one of them disappears. And you know, at the time scale that is going at, the time lapse that's going at, it just goes poof. But in fact, that was a complex process, and the important point from my point of view was that it went away cleanly. It just disappeared and didn't leave any sludge left over. So what am I doing here? Oh yeah, all right. Well, so again, artificial life, birth plus finite resources means we need death. So how should digital organisms die? You know, the inclination, just like when you're writing traditional code, is to, you know, I want to focus on the case where it works. And the error handling, you know, the cleaning up, the freeing the memory and stuff, you know, I get the garbage collector, get something else to deal with that. That's not the fun part. But we absolutely have to care about it, especially in these distributed cases where the stuff is all over the place. And if we don't coordinate the shutdown, who knows what happens? And we'll find out what happens. So that's the reason for actually caring. All right, so the history of death, you know, death has been around for a long time. You know, the point is that as I've been working on the Movable Feast machine for, you know, a decade, coming on a decade and a half now, you know, figuring out how to clean up, figuring out how to die cleanly has been an issue all the way through. So let's take a quick look at the history. The bigger these things are, the longer it takes, the more chance there is that something will mess up. Mistakes happen. Ooh. Now, I'm extremely proud of that. Because it didn't go insane. It didn't end the universe. It actually cleaned itself up. Let's try it again. So that was the 2D printer demo, or an early version of the 2D printer demo, and we weren't actually cleaning up the entire structure, because the thing that was copied in the 2D printer is fundamentally passive, whereas what we're going for now is a cell, a live operating structure that's going to copy itself while it's living, and it's a different sort of approach. Now, last year in 2021, I was focusing a lot on these plates, solid rectangular things that filled the universe and provided a local 2D coordinate system, supported hierarchical nesting, plates with subplates inside, and so on. And they had a pretty sophisticated system of dying. It was a very high priority process. Very early in each event on a plate atom, it was like, am I supposed to die? And if I am supposed to die, are my neighbors supposed to die too? And there were these two key death bits that every single atom that was representing part of a plate had to implement. One that said, yes, I'm supposed to die, and all subplates I contain. My plate is supposed to die, and any subplates I have, I am supposed to die, and any plates that contain me are supposed to die, which is really scary, because you can then go from a small thing and then out to a big thing and then eat it all up. And we can put those together in various ways. And that worked fairly well. Now, so far, I have resisted putting I always just sort of imagine in the back of my mind, I'll just put the death bits from the plate into the hard cell 3 context and so forth. So far, I haven't. We shall see what happens going forward. This year, it's this, in the case of the plate, there was sort of a 0, 0 and a max X, max Y, but there was nothing really central about it. Actually, nothing central about it at all. It was in the corners. Whereas the diamonds have the root in the center. The leader is in the center. The decision about what direction to go next is made in the center. And the idea is, in death as in life, follow the leader. And so that's what I've implemented here so far. Now, that leads a question about what do we do about things that aren't the hard cell grid, but they're in the same space. They're occupied within the domain of the hard cell grid, even though they're not hard cells themselves. The obvious example so far is the pocket chains. What happens with them? Well, let's take a quick look at an example before we get too long here. Okay, so this is a diamond that I have confined by putting a wall all the way around it like that, so it can't actually go anywhere. And we can let this thing run, and if we zoom in here. This is the root all the way in the center, and it's got 4 little lines going in each direction, and those are the contact warnings that are saying there's contact warnings in all 4 directions. So the root, when it wants to move, it says, I can't move. There's no direction to go. So in fact, it doesn't move. Now we can look in what's going on. And it's got this mroot watchdog, which is a timer that's that gets reset every time the root moves. The root is not moving. The counter is up to 5. It's going to go to 6, 7, 8, 9, 10. No, it's still at 5. But each step takes about twice as long. So we still have a long way to go here. We're not going to sit and wait for it. But we can kind of simulate it, right? But we'll just come in with the eraser like this. Let's zoom back out again. All right, so what would happen eventually, and this is what did happen in the demo that we saw, is that one of the root will eventually time out, and it just erases itself, and we get something like this. The HC3 grid is all gone. The pocket chain is gradually cleaning itself up. It's taken a while, and the membrane all around the edge is gradually cleaning itself up also, and it's also taken quite a while. All right, there it is. And now there's just this one tiny little bit of pocket chain left. That might actually be a bug. We'll see. Well, but that's the question. What about the guests? What we're doing at the moment is we're just saying, go ahead, not worry about it. We'll probably need to revisit that. All right, so here's the title card, Engineering Digital Death. And the idea is you go for the root, and once you take out the root, the rest just takes care of itself. All right, So the goals, you know, we missed a little bit. The loop operation's not quite so clear. The HC3 demo, not at all. But we got this quadrant stuff working. Dave's late news. Well, number one, we're going long here. Got rid of so the main point is, you know, we had a Living Computation Foundation nerd who donated a long time ago, and I never got the email out. I finally shipped the email for our newest Living Computation Foundation nerd. Thank you very much. Our next demo will be September 13th, 2 weeks from today. The goals are a loop reshaper demo. That's different than loop operations, to get something about HC3 sequencer, at least designed, something on paper, written down, and have some fun. Thank you so much. I will still be here once again after I get the render going. Thank you so much for taking a look. I hope to see you next time. All right. Well, it went long, but you know what the heck, we'll live with it. So I am going to stop the recording. I'm going to take a quick whatever. I guess I'll rerun the waiting room for a little while, and then I'll be back. And if anybody wants to chit chat or whatever, then we can do that until the top of the hour. Okay. T2 demos. T2 demos. T2 demos. This is the first test to try to do time-lapse with the X-T4. There's the parameters. We're going 300 times. Speed up, these are JPEG frames. There's lots of problems with this, but it's fairly encouraging. I'm worried, since this is just one power zone, I'm worried about when we get to like 9 power zones, whether there's going to be enough res. But we'll see in the second demo where I do some camera projector automation, I'm calling it, that it looks pretty good. We can push from here, we can push all the way into a single tile after the fact and still like read the text, for example, which was not really true with the previous solutions. I don't know if that will still be true with 9 power zones, but we'll see. So this was a big update of almost everything, because I hadn't had this grid fired up for quite some time. I'd been working on the single ring, and then obviously just doing a Hugene run, which I wanted to run until it settled one way or the other all by itself, but I didn't really understand how the Fuji X-T4 works, and its battery died. So that's where this simulation ends. All right, so here we are pushed into a single video, also with a little bit of color grading, since the background of the CDM menus really should be brown. And the LCDs we're using are really so low quality. So I've just tried to get this to approximate, to sort of emphasize rendering what passes for true colors on the LCDs, and let the the T2 tile cases and the surrounding environment and stuff go hang. But I'm also, and this is using the Kdenlive transform effect with keyframes that are set to smooth, which is cubic splines, I think, and I'm starting to get them working. You can see that this is actually fairly smooth, and it doesn't have a lot of changing in directions that don't make a certain amount of sense given the action on the screen. So this is it. This is the first test. I've now got an order for one of these dummy battery things that connects to a charger so that it's not relying on USB power. So hopefully we'll be able to do much longer. Lots more stuff to do. Just figured I'd put the first test up. That's it. I thought I'd check back in on the simulation. Uh, the the CPU fans are going to come on again, and it's going to be a horrible noise. But for a few minutes, we can maybe. Uh, yeah. So SF is the shapeshifter element, which is the replacement for new grow, the thing that was doing the growing the loop last time. It's a re-implementation. Well, it's a lot of copying. But it seems so. Its intention index is 1, and it's suspended. So that's its actual problem. But I think actually the suspend watchdog timer is counting. It's all the way up to 9. So I think in fact this. Well, we'll see. I guess eventually this thing. So the growing stuff is already tricky all by itself, in the sense that we've got to uh, we've got to see stuff outside the event window. We've got to find out if there's a path that actually closes around. And then we have to build the new superstructure, the 3, to replace the 1 when we're growing the loop larger. Thank you. In multiple steps. We can't do it all at once. So there's a time when the pointers, forward and backward pointers in the pocket chain are inconsistent. And we have to, there goes the fans. Well, so be it. We have to avoid the case where they, things that we're doing surgery on, we have to keep them under anesthesia until we finish rearranging the pointers again, which takes multiple events, which can be separated, arbitrarily by other stuff going on. And so that's what the shapeshifter has an M suspended, a data member, a Boolean that you can just say, please suspend yourself because I'm about to, I'm going to do surgery on you, so you need anesthesia for this. But in this case, we killed the root, everything went to hell while this particular one was under anesthesia, so it's still there. But look, now the timer, see, it's not really completely dead. The suspend watchdog timer used to be 9, I think it used to be 9, and now it's 10. And so I think when it reaches 11, or maybe when it reaches 12, I can't remember exactly. It'll take forever. We probably won't be able to wait for it. And that's actually one of the real problems with timers in general, that it's really hard to set them in any sensible way. The X timer structure is essentially random. Each time the timer counts, it gets half as likely to count again, so it gets slower and slower and slower, but it doesn't actually count to 256 and then 512, because that would take a ton of bits to remember an exact count like that. So instead, it just throws a random number: 1 in 256, count; 1 in 512, count; 1 in 1024, count, and so forth. There's various modifications on it, but so it's very noisy. But even if it was exact, even if you could put in, please wait for, 1,000,006 events, on what basis should it be 1,000,006 rather than 500,000 or 10 million? Because everything else is randomized. It's unclear exactly when the thing is going to go off. So in general, I try to avoid using timers in critical roles, and that's why it's watchdog, backstop, and they're set to be very, very generous, because the thing that actually is the most damaging is if one of the timers goes off and it shouldn't have, when things are actually going fine, but the thing just happened to count really fast, and it then messes up stuff that wasn't messed up to begin with. So this is a case. I'm not exactly sure what the right best fix is here, because certainly there will be suspended elements in as long as we're keeping going with the suspended structure. I mean, I guess it's possible that if for the specific case of recovering from a suspension, Well, I guess there's two possibilities. One is maybe even under anesthesia, we should see if we should die. So if we discover, for example, we're not in a pocket anymore, maybe we should check out whether we're suspended or not. That's actually probably the right way to go with this. I'll have to go revisit it. And again, it fits the general pattern that dying, it needs to be an extremely high priority process in the flow of control through a given event. One of the very first things you do is say, are the external conditions such that I need to die? And if so, all the rest of this issue is moot. Whether I'm suspended or not, as far as taking care of my pocket chain neighbors, is way down the list of if I am now on the surface of the sun and the only thing I need to do is see if there's anybody else I can tell them to die and then die myself. That's probably the right answer there. Anyway, we'll let this continue to run, I guess, and you can always just check back in later. Although, yeah, this is the weird thing. If I don't have MFMS on the screen, I don't think it actually, it doesn't update the display. It's still actually running, but now, you see, I can't really tell, but I bet that that display is no longer updating the counts and everything like that, because, you know, it's being efficient, and so the shapeshifter might have completely disappeared. And a new folks. Say hi to Mike Rizzo. This is let's say, a fundamental research and development project. So the near-term goal is to do this A-Life challenge, so to actually get it so that we have code that can be running and doing the whole thing to reproduce themselves. But that is actually, that's, you know, and I've sort of best known in the academic history for artificial life stuff. Well, known for various little things. But artificial life stuff is one of the things that I published some stuff in that has gotten some citations over the years. Neural nets, computer security, blah. But in this case, the artificial life is still a means to an end. The hugely ambitious super goal is to have, once we have cells like these diamonds that can reproduce themselves, that can start talking amongst themselves and, you know, maybe building ad hoc networks of things between them, that could eventually be a more robust, a more scalable basis for general, well, maybe not general purpose computing, but for real-time system control. Robots, cars, processing loops, and so forth, where we're currently using traditional CPU and RAM models of architecture, which are extremely fragile and extremely vulnerable to computer security problems, all sorts of problems, which is fine if you're just sort of playing solitaire, but it's not so fine if you're driving a car or if you're controlling a chemical plant or what have you. And the vision, the long-term vision, is that we take this distributed, bottom-up, inherently robust, structured at many levels, so it's rip-stop rather than brittle, and get enough design experience with it that we can actually build useful stuff. We could build system controllers out of this stuff and maybe have some reason to actually trust them, maybe have some reason to actually think it would be okay to deploy them in control of resources. In control of, you know, tons of metal. You know, putting conventional software in control of cars is, you know, like that. Now, you know, it's true, I've spoken to folks who work at Tesla or who worked at Tesla, and, you know, it's not like it's one giant PC inside the Tesla. Tesla has zillions of small ECUs, engine control units, and little things monitoring this and that and so forth. And that's in general good because it's moving towards a more distributed, that, you know, even if you lose those things, this other thing continues to work. You lose the entertainment center, the brakes continue to work, and all kinds of good things. But it's still the case, you know, that they all get welded together on the CAN network or whatever it is that it happens to be using, because it all has to be able to be updated, which means there has to be a single bottleneck that you can push new code through that gets to all of those things. So, to make a short answer endless, you know, it's a research and development project. The specific goal, the short one for January, is Grandchildren for the Ancestors, show program-driven reproduction in this model. The long-term goal is to build a path to use utility for controlling doing real-time system control using this kind of architecture. We shall see. I may not see it. The medium-term goal for me, for the T2 tile project specifically, is to get this area enough fleshed out that it could become a fundable research area for government and industry. You know, the Intels and AMDs and NVIDIAs of the world, the DARPAs, the NSF, and the European agencies, that folks will get interested in saying, you know, well, you know, maybe we could do this a whole lot better than the T2 tile project, but still keep the fundamental idea that you're building a hardware tile that you have to be able to plug together arbitrary numbers of them in principle and have the same mechanism work. You can't have a 640K limit. You can't have a fixed universal address for each node. None of that. If we can get enough folks inspired, interested, funded to explore that design space, good things can come from that. In particular, a more robust computing base, a more trustworthy computing base, as well as a better understanding, I think, of living systems ourselves and how we compute and exist in reality. And I think that's actually useful all by itself. Is that long enough term for us? Yeah. All right. So, how are we done? Did we? Oh, see, there it is. Somewhere while I was yapping, the last shape shifter, its suspend watchdog timed out. It woke up and it cleaned up after itself. Well, it could be worse. All right. So, we'll stop that. Well, so that's good. So I'm glad that it actually did once it woke up. But I think I'll go back and I'll change it so that more, just like it happened with the plates, move the level of conditions that are death worthy, move them earlier in the event, so we won't have to wait for the suspend watchdog to go off in order to clean up in that particular event. Anyway, all right. So how are we doing with the render? Render has got 4 minutes left on it, so we'll probably be uploading before we get to the top of the hour. Some could be worse. All right, and I guess I will mute the microphone again. And so what was Ben saying? At least it should not affect neighboring diamonds since they still. I see. Right. Yeah. You know, in the current implementation, the membrane is not that Boolean. You know, if you look at it, it's kind of fuzzy, and sometimes it has little gaps in it and stuff like that. So you know, the quality of the edge, the reliability of the membrane inside, membrane outside, would probably, you wouldn't want to lean on that too hard, put it that way. And again, this is sort of rather than trying to find one sort of completely clean edge and then making everything depend on that. It's something that we want to. So right now, the HC3 grid itself looks toward the center. It knows, I am at 7 hops, that guy's at 6 hops, so he's closer to the center, so the center is that way. And that works great as long as there's no HC3 from a different grid that might be getting close enough so you'd say, hey, look at that, there's a HC3 over that way, and it'll just start pointing in the other direction. So what we have at the moment is the HC3 grid, which strictly believes in hop count to say which direction is the center, so therefore which direction is the root, therefore which diamond am I part of, plus this stuff called mbase that fills in around the edges of the last layer of the grid, and then the sensor stuff, and now also the mtip stuff that goes on the very corners, all of which serves to essentially make it a buffer so that it's difficult to get the HC3 from a different grid close enough to confuse the HC3 grid that we've got here. And that's all, fundamentally cooperative in the sense that, when these things are getting pushed together, there's nothing actually stopping them except for the fact that the contact warnings go up to the root, and the root is programmed not to head in the direction where there's a contact warning. But if, something blows a hole in it or forces them together, any number of things, yes, stuff will still go wrong. And so then the issue is, can we limit the damage? Can we avoid having, some kind of Ice 9 thing that will just go out and kill absolutely everything? As Ben says, erasers might still get through because the membrane is not 100%. You can't lean on it for everything. But, we'll see. And, on the one hand, it seems kind of, relying on cooperative stuff seems like, wow. It's not a very robust, not a very safe. You're just saying, well, I see I have contact warnings to my east, so I'm not going to go that way. And the other thing says, well, I have contact warnings to my west, and I'm going to keep on going. But it's not possible to be 100% safe. The low-level physics fundamentally is symmetric. This cell can't know that cell is running some different code if it can't see it, but the code has to exist, it has to be there, and if this one doesn't know, if this one can't know the other one's running evil code, the evil one can't know that this first one is not running evil code as well, so it'll end up being a clash of evil versus evil, and they'll both destroy each other, and everybody goes to hell. So, I spent so many times trying to figure out a bulletproof mechanism for any of these things, for death, for object self, non-self distinctions, for moving large objects that across multiple events and so forth. And I just have to just keep learning that there cannot be guarantees. There never were guarantees. The alleged guarantee of deterministic execution that the CPU and RAM gets us is got an asterisk in the end, and all of the stuff that we're going to build here is going to have asterisks on it as well, but we want to have it as much as we can fail soft and respect the fact, respect space and time. That stuff that's closer to me is more important than stuff that's further away. If I'm not sure about something, I'm going to work to try to keep it further away. The analogy I give in one of the papers way back when was like, it's like computer security, it's like cat security. The cat is touchy about who it lets near. And because spatial distance is your biggest single friend as far as defense is concerned, but if the cat then decides you're safe, it'll groom itself and it'll start grooming you once you're allowed in. So keeping bad things away from you and trusting things that are closer to you is pretty fundamental to the idea of existing somewhere in space. So we'll see. Erasing swap lines inside the cell could do the trick. Well, maybe, but then pink bathtub ring. How do you clean up the swap line? Where does that end? It ends at the membrane, or it ends at the HC3, or whatever it happens to be. I think probably the thing to do is to have the HC3 as they are spreading, as they are doing their flooding death, is to have them go ahead and erase the pockets around them before they erase themselves. And again, there's no guarantee there, because there will be events happening that are in pockets that haven't been reached yet, but they'll be able to see that their pocket is incomplete. So the pocket container, the pocket inhabitants, actually there's a class, there's a base class in API called Pocketable in the current code base, that everything that's going to live in a pocket inherits from. So all the pocketable stuff will still need to deal with seeing a partially incomplete pocket around itself, and it's going to have to, again, make decisions to help out in the cleaning up. But probably the single cleanest thing to do, the thing that would get us close to the movie, the science fiction movie, the Tron thing, where someone gets hit with the glowing frisbee and they just go boop. I don't remember what happens, but I bet it's quick. When something dies in Tron digital space, it probably goes poof pretty quickly. I don't know if anybody else remembers, but on the one hand, that's what the engineer, the top-down, keep control engineer in me wants to do. Wants to, this entire space is now verboten, wipe it out as we clean up behind ourselves. But on the other hand, to be able to say, what if, like we've grown a daughter inside us, what if we could say, the outer membrane now wants to die, and it would just use the death mechanism to wither away and leave these pristine little daughter and reconstructed mother behind. That would be very nice. We'll see. Whoops. Oh, geez. I talk so much. Ben, thanks for coming again, and thanks for asking the questions. Mike Rizzo, thanks also for the question. It's the top of the hour. I am going to stop the stream and get the, actually, right, I didn't even, right, the rendering's done. I got to get it uploading. Okay, hope to see everybody in a couple of weeks. That's going to be it. Where are we? Here it is.